Hi everyone, welcome back to our third day of the Open Science Room program at OHBM, and we're very excited to welcome you here today from everywhere. So welcome to our global community joining from the OHBM platform, but also from our multiple streaming platforms. So today the theme is past, present, future of neuroimaging and open neuroimaging. And we'll start with this session of lightning talks. And just a quick recap, you can see on the screen there are some links. You can access more information about this theme, about the schedule, and about the speakers on our website. If you want to, you can share your exciting comments on Twitter, and we've added some hashtags there for you. You can also join the discussion now and later on Mattermost. We have a general discussion channel there, but also a discussion channel that's more particular to this theme of the Open Science Room.
So first up, our lightning talks. We'll have some reflections on where we've been and where we think we're heading in open neuroimaging. We've got 4 talks of 5 minutes each, and then we'll have 20 minutes of Q&A with all speakers together. And some speakers will be available for live Q&A in your time zone, but unfortunately not all speakers are likely to be available at the same time. So if you have questions for speakers who aren't here, we'll endeavour to pass those on to them.
So we'll use Crowdcast as our main platform for interaction with the global community and also for questions. So if you're using Crowdcast, please post your questions there and upvote them so that we can pass those on to the speakers in the live Q&A session. You can also post your questions if you're joining from the OHBM platform via that route. And if you're unable to post your questions in this way, we can also have a discussion further on Mattermost. We would love to get your feedback on the general OSR experience, but also feedback for the speakers themselves. So please fill in our feedback polls that we'll post for the session. And then also please remember to be kind and respectful to each other. When we all registered, we agreed to abide by the code of conduct. And we encourage you to, if you see or experience any violation of this code of conduct, to report that using the reporting structure that's detailed in the code of conduct, which is available on the OHBM website.
Now it's my pleasure to introduce our speakers for this session. First up, we'll be hearing from Gael Varoquaux, and he'll be talking about the Open Source Imaging Initiative, followed by Loïc Terrel, and he'll be discussing Neuro Libre, which is a cloud-based and curated repository for Jupyter notebooks in neuroscience. After this, we'll hear from Robert Cox with a retrospective of AFNI from then to now and beyond. And finally, we'll hear from Gael Varoquaux discussing NiLearn as an open, easy, and powerful statistical analysis of brain images. So thank you again for joining us, and we look forward to hearing these talks and to continuing the discussion in the Q&A. Thank you.
Hi everyone, my name is Gael Varoquaux. I'm here to present the Open Source Imaging Initiative, OSI. OSI advertise and implement open source practices for software and hardware in research and medical technologies in magnetic resonance imaging. Currently, I'm finishing my PhD in Berlin, Germany, regarding diffusion MRI applied to the kidney. As many of you, I faced many obstacles during my PhD. Sometimes to overcome these obstacles, you need to come up with new methods or new ideas. While I was reading this paper in a different field, I found these really cool methods that I would like to implement. However, if I need to start to implement this method from zero, it would take me thousands of hours that I didn't have. I was lucky because I found an open source tool that I could use and I could adapt to my needs. And with that, I could solve my problems with only a few hours of coding. With this, I found the benefit of document and make your work available to the others. And this is just a small example, but in the same way, the open source concept can be applied to a larger scale. Let's take a look to the world map of coverage of MRI. As you can see, MRI is not accessible in many parts of the world, mainly because it's an expensive technology. And I'm not just talking about the initial purchase price, that is the most visible one, but all the under the water prices. So the user training, the repairs, the regular service and maintenance, all these contribute to this very expensive price. But if we apply some principles of open source and innovation, we can lower these prices. So as a community, we can build an open source system that is more accessible to everyone. By applying innovation, we can customize this system to the clinical application rather than have a universal system. By having access to the documentation, we can do in-house maintenance and not fly someone from a different continent to repair the machine. We can also educate and train the users for this system, and we can also customize it to the local environment. The first prototype was already built based on permanent magnets. It's a low-field MR system, but this low field, we can achieve this image. It's a knee image with a common turbospin echo sequence, and it was acquired in less than 12 minutes. So this is the reality, and the vision of open source imaging is this. But what is exactly the OSI, the Open Source Imaging Initiative? It's a platform that tries to give visibility to open source projects in MRI. If you go to the website, you can find more than 60 open source projects divided by hardware and software. If you click in one of the projects, you will find a small description of the project, the main contributors, and the contact of the main author. If you want to replicate this project, you will find all the costs that you need for the material and all the resources that you need to replicate the project. You can also find the publications that were originated through this project in order to replicate the same results as the author. We also launched a wiki in order to connect the software expertise with the hardware expertise. We also will include some educational material. So if you have an area in MRI that you feel comfortable, that you have an expertise, please feel free to join every Thursday at 5 p.m. in this virtual room. We use this hour to write a paragraph or a few sentences about our area of expertise, to share this knowledge to the others. Last year, we were together with the École Polytechnique of Montreal, we organized a marathon, a hackathon for MRI professionals to promote reproducibility and open source practices. So if you are interested by this project and you have some ideas that you want to share, please join us or contact us. Thank you very much for your attention.
We are pleased to introduce Neuro Libre, a curated cloud-based repository for Jupyter notebooks in neuroscience. Open science practices are gaining wide adoption, fueled by concerns about access, reproducibility, and transparency in the peer review process. Traditional publishing is slow to adopt open science practices. Access to publication is not free, reproducibility is difficult, and increased interoperability is needed. This is where Jupyter Notebooks can facilitate, being a popular alternative to static PDF, embedding code and figures in a single document, and offering a standardized interface to reproduce figures from data. However, the neuroscience community could still benefit from a created platform to publish such notebooks. That is why we created Neuro Libre, a curated repository for Jupyter notebooks that offers technical review, free long-term preservation, and reactive computational resources. Neuro Libre is a community-driven project initiated by the Canadian Open Neuroscience Platform. Anyone with basic development skill can submit their research object to Neuro Libre using Jupyter Notebooks. The research object are screened for one of two streams, companion to a published or preprint article, or training material for an educational workshop. Our publication workflow follows specific structural rules. After the user fills out a Google form, our bot performs basic sanity check on the notebooks, followed by a human technical review using the GitHub platform, where the published notebook will be hosted. Finally, the user is provided a web link listed on the Neuro Libre website to share results with the community. Here is an example of a Neuro Libre publication hosted at neurolibre.com. The notebooks are rendered using Jupyter Book for a unified look and an interactive user experience. The Neuro Libre backend infrastructure is most notably built on Binder Hub technology. Its dependencies are open technologies that are well established in the academic community. Docker images for the environment reproducibility, Kubernetes for the user resources management. We are not alone in this adventure. There are several publishers that are willing to work with us, including the new OHBM open publishing platform Aperture, magnetic resonance in medicine, and PLOS computational biology. We are grateful to CONPI for the financial support, as well as to Cancer Computing and Compute Canada for the infrastructure support. Please remember to check out our website, neurolibre.com. Thank you.
Hi, this is Bob Cox. I'm going to tell you a little bit about AFNI, where it came from, where it is, and maybe even something about where it's going. So this is the AFNI origin story. You can read this. You don't really need to read the slides themselves. But basically, it was one of those random bounces that happens when you play life in like a pinball machine. You know, you bounce around and things happen to you, some good, some bad, and this turned out to be pretty good. So AFNI was born in 1994. Well, at first, AFNI was just for dealing with fMRI data, the simplest kind that we now know and love. And it did some basic stuff that everybody and their mother can do now. And that was how I intended it to end. I got it working, and it met the needs of the neuroscientists, and I said, I don't want to do this for the rest of my life. Never say that. That's my advice. So fast forward 26 years, and AFNI didn't end, and I have been doing it for, well, maybe not the rest of my life, but a good fraction of it. And now I'm going to just give you one more example of complicated analyses that we didn't even dream of back in the good old days. Resting state data analysis. Resting state data analysis is not so easily tied down to external data. It doesn't have task timing, and so it should be correlated in some way with something else. There are lots of different ways to do that. One of those is an example I'm going to show you now, to Diffusion Tensor Imaging Tractography. So what we have here is a display in the summa portion of AFNI of a cortical surface, and we have colorized resting state correlations from a seed, and then inside we can see the tracks that pass through the same seed ball, which you can see moving. The seed ball is moving down from the back of the brain to the front of the brain, and you can see the tracks that pass through the ball and the seeds of the correlation from the corresponding part in the folded away cortical surface. This was all done interactively in AFNI just by clicking and capturing screen images and then animating them. This really was actually quite easy to do once 5 to 10 years of software was developed. All this can be scripted as well. So beyond the present, AFNI could be used inside other projects. The programs, it's not one monolithic monster program, thank God. Programs read data, do stuff, write data out to disk, and end. So that you can use these as components in bigger projects. You can add other things that open source can be used for or can contribute to AFNI as data, atlases, templates, stuff like that. Data formats. AFNI reads a bunch of common data formats, but we are happy to take on new data formats. And even more valuable is simply people giving us suggestions for features. Some people often don't ask for features. They say, why can't AFNI do this? But sometimes it already can, or almost already can. And other times it isn't very difficult. If you're from outside, you don't know what's easy and what's hard for somebody to do. You may ask for something you think is easy, and it's a killer. You may ask for something you think is hard, and it's like, oh yeah, I have to add 3 lines of code. One final thing I want to say is that in the fMRI world, there's a recurring thing every few years. There's some sort of panic about someone posts a new method, and they say my analysis method is the best, and yours is wrong, bad, and evil. Most of the time, this is really exaggerated. These haven't been tested thoroughly. They're not so well documented. Do we have to tear each other down? Finally, here's the floating heads of the current AFNI team. Mine, I think you can see in the presentation, and that's about it. Thank you.
NeuroImaging is a toolbox for statistical analysis of brain images. Its goal is to facilitate analysis that are versatile and yet approachable. It provides tools for a powerful scripting environment, blending data processing and visualization in a reproducible way. Its functionalities range from classical statistical tools for brain imaging based on the GLM to advanced models with functional connectivity and machine learning. NeuroImaging is a Python tool. As a consequence, it is free and benefits from a wider ecosystem. For instance, it can be combined with DiPy for diffusion imaging, or with stat models, PyMC3, or scikit-learn for advanced statistics. Let us show you a few functionalities of NeuroImaging. For instance, functional connectivity. NeuroImaging can extract functional networks from brain activity using various parcellation models, ICA, or dictionary learning. It provides tools that extract time series given regions or networks. With those time series, it can build a connectivity matrix and compare these across subjects.
NeuroImaging can project and visualize data on the surface without the need to install any additional software. There are also many ways to represent volumetric brain data. The most concise visualization is probably the glass brain, which doesn't require the choice of cuts. And NeuroImaging has interactive visualizations, which for example make it easy to scroll through the cuts. There are many options and possibilities to combine visualizations to produce publication quality plots. These can be exported to various formats, including PDF or SVG.
We can use NeuroImaging for decoding, where we show a brain image to a supervised learning model and ask it to predict an associated variable, such as the underlying mental condition. A classical example is the HAXB dataset, where we have fMRI scans and we have to predict if the subject is watching a face or a house. Decoding is a difficult learning problem because we always have few samples in high dimension, and for dimensionality reduction we can use decomposition methods such as dictionary learning, feature aggregation using parcellations, or feature selection, either as a pre-processing step, for example with analysis of variance, or by adding sparsity-inducing penalties to the learner's cost function, such as the elastic net or TVL1 penalties. With NeuroImaging and scikit-learn, we can easily implement a full decoding pipeline, including model selection and validation, and it will get even easier in the next release with the new decoder module.
In its next release, NeuroImaging will integrate new statistical modeling abilities that used to be available in NiStats. Objects first-level model and second-level model let you perform subject and group analysis on your images with all classical statistical methods. This is designed to make analysis transparent and easy from start to end, with functions to plot event files, create and visualize design matrices, and integrated reporting of general linear models that are fitted. And personally, I find it very useful when I try to work on a new dataset to be able to assemble a pipeline to clean it, feed GLM, and run decoding on their output with only a few lines of code.
NiLearn is a use case-driven software, which means we provide documentation that's geared towards different user use cases. To do this, we provide 3 different levels of documentation. We provide a user guide, which gives a high-level overview of different common neuroimaging workflows and how NiLearn can help support them. We provide a reference or API documentation, which describes particular details about function calls in NiLearn. And we also provide an examples gallery, which intermixes narrative text, code, and outputs in order to help users understand how they could implement particular analysis workflows in NiLearn. So, for example, if we look at the introductory tutorial to fMRI decoding directly accessible from the examples gallery, you can see this standard structure. We also make a point to provide interactive outputs, as we find this often helps users to be able to understand what's being done and what particular data structures look like. So here you can see an interactive image visualization, and you can also see a generated report for a nifty masker object, which is a commonly used object in NiLearn workflows, which includes both a visualization of the object as well as the exact parameters provided to its call to provide more transparency for users in understanding what this object has done. But it's not just enough to have this available in the browser. We'd also like for users to be able to manipulate it. So here you can see that we provide both the raw code for users to be able to download, as well as a Jupyter Notebook. And we additionally provide a MyBinder integration so that users can run the example in the browser on MyBinder infrastructure and be able to change different parameters or work with different data sets.
NiLearn is built by a broad community. It is an open source project, and contributions come from all over the world. We have a strong quality assurance through the process, based on software testing and technical discussions. We believe that our community is key to the future growth and success of NiLearn. It brings forces by assembling many on a common project, but more importantly, uniting all our diverse expertise creates better tools. Use NiLearn. It is free, it is approachable, it is powerful, and join us to make it better.